All right, I don't know if you watched the video I asked you to watch at the very beginning when we were starting trig graphing. I think it had like the harmonica playing, and it was really kind of fast-paced little showing you all the different ways that trig modeling can be used. This is just a slide of tides, and it shows how the tide coming in and out is very sinusoidal or shaped like a sine or cosine graph. Okay, a sinusoidal function means it is like a sine function in that it can be shifted, stretched, or compressed the same as a sine function. Okay, in physics, anything that oscillates like a sound wave, alternating current, can also be used. Now you have to be really careful that the word sinusoidal does not mean it has to be a sine. It can be either a sine or cosine equation that is used. Most often, it's actually easiest to use, I would say, the cosine version a lot, because cosine, you could almost always, they're going to tell you where a maximum is, okay, where the maximums and minimums occur. So that would help you to write an equation for real world data. I'm going to give you the story today, not even the graph. You're going to have to write the graph too, or draw the graph too. So the first one says, as Rashad rides a Ferris wheel, his distance from the ground varies sinusoidally with time. When the last seat is filled on the Ferris wheel, he starts in the position shown right here, which is middle of nowhere, up a little ways. And then he is moving up. Okay, it says going this way. And it takes him 3 seconds to get to the top. So at time 3, he is at the top. That's why I'm saying this would make an easy cosine graph, because we know where that starts. We don't know where he was when he started this story. We're going to have to figure that out later. I do want to show you super quick, if it'll load real quick, just the idea in case you don't remember what we're talking about here. This is a Ferris wheel. So if you're this red seat, this one's moving the opposite direction of Rashad's, but see how it goes up and down, and then up, and then down, okay? But notice, it never hits the ground, okay? So, the idea is that it's going to go up like it did here, and then it's going to go down, and then it's going to go back up, and then it's going to go back down, okay? And it's never going to hit the ground. If Rashad's seat hit the ground, he might hurt his legs or lose his legs. I don't know. Okay, so T is going to be the number of seconds that have elapsed since the Ferris wheel started. Rashad determines it takes him 3 seconds to reach the top. So at time 3, he's at his highest, which is 43 feet above the ground. Okay, 43 feet up. So when he's here, the distance all the way to the ground is 43. Is that whole way down. He also determines that he's back at his original position after 8 seconds. Now, I don't even know where it was that he started, but if it took him once around to there to get 8 seconds, it's going to take him once around starting here to do 8 seconds as well. So this makes, it says 1 revolution takes 8 seconds. That is the period. So if this was at 3, 8 seconds later, at which would, that's supposed to be seconds, 8 seconds later, which would be at 11 seconds, he's back at the top again. So he was at the top at 3, and it took 8 seconds till he got back to the top. I hope this is making sense. Now, this is a little bit of craziness that I need you to understand. The diameter of the wheel is 40. So all the way from the top to the bottom is 40. Well, that's good, because remember we said we didn't want him to hit his head on the ground or his feet. So there's 3 feet of clearance at the bottom to make this 43. So the lowest he ever goes is 3, which makes the distance from the top to the bottom the diameter of 40, or the radius of 20 actually tells us how far above the middle he goes. He goes up 20 here, and how far below the middle he goes. He goes down 20 here. Well, what is how far above and below we go called? When we're doing trig, it's called the amplitude. Okay, so we just figured out that the amplitude is 20. The period was 8 seconds. And we need to find the midline, which is exactly 20 below 43, which would be 23. And it's exactly 20 above 20, or above 3, which would be 23. Or you can add those and average them. 43 plus 3 is 46, divided by 2 is 23. But you got to remember that's actually the vertical shift is up 23 because it's the midline. So that's our K value. All right, I'm going to call this a cosine because it's easiest to see where the peak is to the next peak. Because I don't know if he started at the bottom. If he didn't, he started in the middle here of nowhere. I don't know if he was above or below the midline. Looks like he was below, but we won't know that until we write the equation here. Could be misleading. Okay, so I'm going to call it a cosine that has shifted to the right 3 units before it started being a cosine. All right, so sketch. What is the lowest you go and why is it greater than 0? Lowest you go is 3 feet above the ground, so you don't lose a leg. That's right, don't hit the ground. Okay, pretend that says hit the ground. All right, what is the equation? So let's try this. The height is, we said the amplitude was 20. We're going to call it a cosine. We said the B value, we forgot to find the B. Nitro, if the period is 8, then B is 2 pi over 8. And I don't care if you write it as 2 pi over 8. I'm going to go ahead and reduce it to pi over 4. And we said we had to shift it to the right 3, which is minus. And then it is shifted up. The vertical shift of 23 goes on the back. That's what's, I don't know why it's so much trouble, but that's what gets students. First of all, they want everything to start. They want to know where it starts on the x-axis, and you don't. You don't know where this is until 3 seconds in. But the second thing is they tend to get the amplitude and the phase shift mixed up on the equation. Okay? Amplitude, the vertical shift here, the vertical shift of 23 through the middle, that goes at the back. How far above and below that, that goes at the front. All right, now we're going to use our calculator, and then we're going to predict what happens at all these different places at time 6, 4 1/3, 9, and 0. So we got to, first of all, make sure we are in radian mode. So we're going to go here to mode and make sure radians is highlighted. If your calculator looks like this, where degrees is highlighted, you need to move it back over to radians and hit enter. It has to, when you go to the top here, say radians at the top of your screen. If it says degrees up there, right up here, you're in the wrong mode. All right, then we're going to type what we just wrote, 20 cosine pi over 4, extra parenthesis in there, x minus 3. Let's get our phase shift in, 2 close parentheses and a plus 23. And we need a window that matches our story. So we started at time 0, and it has to go out at least 11 if we want to see where it finishes that first cycle. I'm just going to put like 15. Watch him ride for 15 seconds of his ride, okay? And then the bottom we can say is 0 because he never hits the ground. And the top, he was up at 43. Whoops, the max here. I'm just going to put 45. All right, I'm going to graph it. So this is his ride. So we need to check if that's right. I'm going to go trace 3. At 3 seconds in, he's supposed to be 43 feet in the air. Bingo. It works, okay? If you wanted to graph the line 23, just to see that that's the midline, you sure could. Remember we said he didn't start at the bottom or the midline, we didn't think? Okay, he started right here in the middle of nowhere, and that's one of the questions we're supposed to answer. So I'm going to go trace, and it's going to ask me, what is his height at 6 seconds into his ride? Now you got to make sure you're on the ride here, and go to 6 seconds, the red path. 6 seconds, he was at 8.9 feet. At 4 1/3 seconds, well, that's pretty specific, but if we do at trace 4 plus 1 divided by 3, it'll give us exactly 4 1/3. He was exactly 33 feet in the air. Then we have 9 seconds and 0 seconds. I lost my calculator. All right, at 9 seconds, he was at the midline. And then the big question, how high was he when they actually started the ride? 0 seconds, he was at 8.9 feet. All right, on the next slide here, I think I put for your notes, make sure it's in radians. I gave you a window. It's not the same one I used when we were just doing that, but that's okay. And here's the equation, just so in case you didn't catch all that when I was doing it. All right, then we have a spring question. This says, a bouncing spring problem. A weight is attached to the end of a long spring, and it's bouncing up and down. As it bounces, its distance from the floor varies sinusoidally with time. So I'm going to erase this in a second, but so it starts bouncing and it goes up and it goes down and it goes up and it goes down and it goes up and it goes down and it goes up and it goes down, okay? So as time goes on to the right, the spring is not moving left and right, but as time goes on, its height can be measured sinusoidally. All right, so assuming that the spring is frictionless so that it doesn't slow down and continues to bounce, it says its distance from the floor, you start a stopwatch. When it reads 0.3 seconds in, the weight reaches a high of 60 centimeters. So at 0.3, it's at its very highest, 60 centimeters. Here, I don't know where it started. I just know where that maximum is at 0.3. Which probably means I want to graph it as a cosine because they told me where the maximum is. All right, it says the weight first reaches a high of 60 centimeters. The next low, which is 40 centimeters above, it says, occurs at 1.8 seconds. 1.5, 6, 7, 8. It's down at 40. And that's the next time it hits a low. Oh. Well, that's not even a period, right? Your graph will not show a whole period. This distance, or time, I should say, of 1.5 seconds is half a period. So we would have to keep going, or keep going this way, but it wouldn't make sense for this to be negative. But if we did another 1.5 seconds on this way, we'd hit the next maximum. But all we really need is to say half a period is 1.5 seconds. So the whole period would take 3 seconds. So our B value is going to be 2 pi over 3. Now, let's see, from 60 to 40 is a distance of 20. So half of that would be 10. So we're going 10 above it and 10 below it. Ugh. So that's the amplitude. The midline between 40 and 60 would be 50, and that goes at the back. I think we got everything. It's a cosine graph. We said the B value we want to use is 2 pi over 3, and it didn't start. Its peak was at 0.3, so we're going to say it's shifted to the right. Oops. 0.3 to get it to be a cosine graph. It obviously was doing something over here, but we don't know what. We just know that its peak was at 0.3, so that's the easiest way to write the equation. All right, now we're going to type this in to the calculator, and we're going to see where it is at 17.2. And what was the distance when you first started? We are going to find where this magically goes backwards here. All right, so I have to clear out both of these, and I'm going to put in 10 cosine 2 pi over 3, another parenthesis, x minus 0.3. Now remember, we didn't show a whole period, but we figured out how long it would take to be a whole period. It would be 3 seconds then. That was the 2 pi over 3. And the midline is up at 50. All right, if I want to set a window, it's not going very fast. I have out to, 2 seconds here, but it asks in a minute us to go to 17.2. So you want to set your window out past that. So I'm going to set 20 seconds. So it's going to do a lot of repetitions in 20 seconds. And up and down, it got up as high as 60. So you could do like 40 to 60. I'm just going to go 0 to 70 or something. Remember, it's going to bounce between 40 and 60, so it's going to be up kind of high on my graph paper. All right, so just to make sure that this is right, I'm going to go trace 0.3, and it should be at 60, okay? And then I'm going to go trace 1.8, and it should be down at 40, okay? I could go to 3.3, because that was the start plus another 3 seconds, and it's back up at 60. Now, it's really hard to tell in this window that it isn't quite at its peak. It didn't start at its peak, but if you go to 0, it wasn't up at 60, it was just a little lower than 60 here. It's like at 58, which makes sense better than my little red line there. Okay, it was like at 58 there. All right, so what are the 2 questions it asked? Is that right there, what is its height? 58.1. When we started the timer, so that would be t equals 0 or x equals 0. And then it wants to know what happens at 17.2, so you'd have to trace all the way out to 17.2. 43.3 centimeters above the ground. If we went out that far and kept watching it do the same thing over and over. Again, friction would actually slow it down, but we're going to go with it's a frictionless spring. All right. Oh yeah, on the next slide here, I have all that for you in the notes. And this time I did do just 1 period. Okay. So I stretched it out with a different window, so then you can see that it wasn't quite at its maximum. But you got to have a window out past 17.2 if you're going to check that value. All right, 2 more examples. A tsunami or a tidal wave has an effect like a rapid change in tide, is a fast-moving ocean wave caused by an underground earthquake. The water first goes down from its normal level, so wherever normal is, it goes down first. And then it rises in equal, however far it goes down, it then goes above the same amount. Okay? That's the idea they're telling us here. But it says the period is about 15 minutes, so we're going to use this for our period, which makes our b value 2 pi over 15. And suppose that a tsunami with an altitude of 10 approaches a pier at Honolulu. Oh, so it's going 10 above and 10 below. Amplitude of 10. So the water is normally 9 meters here, it says, at Honolulu. And the first thing it said it does is it goes down 10. Well, how can you go down 10 if there's only 9 feet of water? Well, think about that. If you're standing there and the water tries to go down 10 feet from below the pier, it's going to recede out, right? You're going to see little critters laying on the sand there because the water has receded out. away from you, and you'll see starfish and maybe little stranded fish and whatever just happened. If you're ever standing there and you see that happen, the water quickly receding away from you, run, because it's about to come back like twice as tall. Okay? I didn't draw that well at all. That's out of proportion. But it went down 10 and it went up 10. So the peak here would be at 19. And the minimum would be at negative 10. Or negative 1, I'm sorry. So the amplitude is 10. They told us that. So we have 10. And, ooh, can't we just call this a negative sign? And then we won't need a phase shift. If it starts here and it goes down, up. That's a little better one. I don't know. It's still not very good. But we could call it a negative sign, and then we wouldn't need a phase shift because the shape is going like this, which is a negative sign. The period, did they tell us? Oh, yeah, we did that already. The period was 15 minutes, which meant a 2 pi over 15 went into our equation. And the vertical shift is simply the midline, or the normal 9 meters of water. All right. I don't know if I can skip typing this in my calculator if we go to the next slide, or if I got to type it anyway. Yeah, I didn't. This is what I did, but it didn't. I didn't show the. Okay. I got to type it in so that we can check all those other answers. So it would be negative 10 sine 2 pi over 15 x plus 9. You could put extra parentheses around the x. It won't matter, I promise. First, we're only looking out for the first 15 minutes, the first cycle. And I guess it doesn't ask any questions beyond that. So we can just do 15 if you want. And remember, it did go down negative, so we need at least negative 1. I'm going to do negative 2. And then it went up to 19, so I'll do 20. There's what it does, okay? The water gets shallower, shallower, shallower. All of a sudden, it's receding out, and then it comes rushing back and goes twice as tall as it was and takes out a whole bunch of stuff. Okay, so what do we have going on here? We have 2 minutes. So if I go trace 2 minutes into this story, the water is only 1.5 meters deep. Is that right? 1.6. Okay, I think it was meters. 4 minutes into the story, it's below almost negative 1. And 12 minutes into the story, I think we're in trouble if we're still standing there. The water is 18.5 meters. Was it meters? I need to double check. Yep. And did this get to 1.6? I don't remember. Meters, meters, meters. Minimum depth is negative 1, and the water recedes would be what I would use, that word. I'm not sure I'm spelling that correctly. All right, last one. I like this. Space one, it says, when a satellite or rocket is launched into orbit from a site such as Cape Canaveral, which is not on the equator, it goes into an orbit that actually takes it alternately north and south of the equator. Its distance from the equator is approximately a sinusoidal function of time. Suppose that a satellite is fired into orbit from Cape Canaveral. 10 minutes after it leaves the Cape, it reaches its furthest north. So it's fired here, and it goes a little bit more north until it's 4,000 kilometers north of the equator. Half a cycle later, it reaches its furthest distance south, 4,000 south of the equator. On the other side of the Earth, of course. The satellite completes an orbit every 90 minutes. So it started somewhere. We don't really know, but we know it was its furthest up north by 4,000 at 10 minutes. And then 90 minutes later, now be careful, this is not 90, and it's going all the way south and north. Okay, it's 90 minutes to here. No, completes an orbit. Just kidding. Let me undo that. 90 from here all the way till it finishes. So this would be 100. This entire distance of 90, time of 90 minutes, is one period. So the period is 90 minutes. So you could put 2 pi over 90 into your equation, or you could reduce it to pi over 45. So I'm just going to call this a cosine. We don't need a vertical shift because it went negative 4,000, and the negative just means it was south of the equator. So the amplitude here above and below is 4,000. And we're going to call it a cosine. We decided pi over 45 went in here, and we started it at the peak of 10 minutes into the story before it was totally at its more northernmost point. Can't say that. 4,000 kilometers above. And then we didn't need a vertical shift up or down because it was going directly 4,000 above and below the equator. All right, so finish this video quickly here by typing this in. 4,000 cosine pi over 45. We needed a shift 10 minutes in before it hit the peak. 2 parentheses, and we didn't need a vertical shift up or down. Now, if we want to see one cycle, it would be out to 100. It does say here we need to check at 163. So I'm going to go out to like 200 seconds or minutes into the story. Minutes, wasn't it? And then it's 4,000 above and 4,000 below. So I'm going to put a little extra so that it doesn't hit the top or bottom of my graph. Just kidding. There we go. So here's the story. And we want to check that at 10 minutes in is when it hit 4,000, and 90 later at 100 is where it was back at 4,000. So our equation is working. It asks where is it at 25, and I have 2,000 north of the equator. Then at 41, it is 2237. I'm just going to round that. South of the equator, and that's why we had a negative number. You could leave the negative, I really don't care, but it's a distance. And 163 into the story, it's 1236 to the south of the equator. All right, last question says, if Cape Canaveral is actually 3154, what happens at time 0? Is our equation a good predictor? Well, we got 3064, and it's actually 3164. So our equation is off a little bit, but if you did a percent of error, it's not off by very much. Okay? And again, I looked this up on the internet, and the equation was just a made-up story probably anyway, but it is kind of cool that it's close. All right, I think that's it. And there's the one I graphed it on my earlier for you. Now you need to do the practice. Again, there's a worksheet of practice, and I only ask for a few of the questions on the key, but or on the slides, but I stress do them all, okay, and check your answers against the key. Ask questions at our next meet.